Okay, hello everybody, and so what I'm going to do is I'm going to go over test three, what you need to know for it. Uh, so I gave you two outlines that to look at and hopefully work on your own. But in regular classes, when I meet face to face, I will do a review of these. So next best thing I'll do since it's online is come up with a little video for you. Okay. So there's two worksheets. In the first one, it says first one says quiz one, second one says quiz two. Actually, they're all into one test, test three. And I used to have them split up into two tests. That was a long time ago. So let's go over them. So if you go to the first one, the very first thing it asks is, what are the three components of test three? Okay, so there should be more than that. All right, so to let you know, um, is there's more than three components actually. The components are going to be carboxylic acids and esters, polarity and molecular interactions, um, and then lipids. Okay, and so the first worksheet just had to do with molecular interactions, polarity, and carboxylic acid esters. Second worksheet has to do with lipids. Okay, so we'll move on to the next slide here. All right, so the first question is draw the function group associated with these two molecules. So these two molecules are known as carboxylic acids and esters. The functional group is a carbon that has a double bonded oxygen and a single bonded oxygen. Okay, a carboxylic acid will have an H coming off of it. So okay, on this side will have a carbon chain which represented by the letter R. And then ester, instead of having H, it will have carbon chain, oxygen, but instead of an H, it would have more carbons. Okay. All right. So what you have to know for the carboxylic acids, know how to name them or draw them. And so there are the first two, which is the first one is this single carbon carboxylic acid, and the second one is is two carbon carboxylic acid. These guys are, well, I mean, if you know methane, ethane, all that, you can draw them. But the thing is that uh, this is formic acid is a one carbon carboxylic acid. Technically, its name should be meth, just like methane. Okay, should be methanoic acid. Okay, but we don't call it that. We call it formaldehyde, and I went over that. But so it's simple like this. Okay, so we don't call it by its fancy name, methanoic acid. We call it by its common name. The two carbon carboxylic acid, its technical name should be ethanoic acid because it has two carbons, like ethane. Let's just spell it wrong there. That should be OIC, acid. Okay, and it's simply, okay, here's the carboxylic end, carboxyl end, and it has one carbon coming off of it, and I'll leave the hydrogens. Okay, so this is two carbon carboxylic. Now, after two carbons, you have to use the specific naming formula. Okay, so if you have three carbons, it's going to be propanoic. If it's 4 carbons, good butanoic, and so forth. So let's draw 2,3-dimethylpentanoic acid. So I know this is 5 carbons. 1, 2, 3, 4, 5. Okay, notice that I don't have to tell where the functional group is because it always comes off in number 1 or the end because depends on which way you go. So we'll put it over here. Okay. So this is number 1 carbon. And it tells me I need to put a methyl on 2 and 3. Okay, so what you have to know how to do with carboxylic acids is to be able to draw them, give it a name, or name the drawing. Okay, so there is a chemistry that you need to know as well, and that's to take to show. We did this reaction last test where we took a primary alcohol, and ethanol is a primary alcohol, and whenever you take a primary alcohol, you can oxidize it to a aldehyde. Well, you can further oxidize the aldehyde into carboxylic acid. And so this is a specific example of that. So the thing is you go from a primary alcohol, gets converted to an aldehyde, and the aldehyde will get converted to a carboxylic acid, okay? Right, and this is a specific example. So we're going to take ethanol. Okay, then what you do is you oxidize it, which means lose 2 hydrogens. And it's going to be, we're going to use this one, and we're going to, I guess we'll lose this one here. Doesn't really matter. So you get, okay, so this is acetaldehyde. And then what you can do is you can further oxidize by adding oxygen. And then what you get, okay. Now over here, you add an oxygen. Okay, so notice this gets changed to this. All right. So that's what you need to know for that one. Okay, so next you need to know next we'll talk about esters. Esters are, like we said previously, are basically the same as carboxylic acid, but instead of having a hydrogen, they have a carbon coming off. And what we do is we learn how to name them by learn how to make them. So what 2 kinds of molecules are combined to make an ester? An alcohol and a carboxylic acid. Okay, and they make an ester, and also they make water. So what is also one of the products of esterification? Water. So what is so it's going to draw this process here, esterification process of adding propanol with butanoic acid. So I'm going to do propanol first. So propanol has meat eaters prefer. So it's 3 carbons. Okay, OH. Okay, and you have butanoic acid. So that's 4 carbons. Whoops. I want to draw it kind of backwards here. So this is the OH, and so this right here is carboxylic acid part. All right, when you combine them, what happens is this pops off here, and this pops off here to form water. And then this is a propyl, and it combines with this thing right here, and this is butanoic acid that's lost in H, so it's a butanate. So so it's going to be 3 carbons, 1, 2, 3. Okay, and then it's going to have this oxygen, and then so it has this, which is a propyl, and then it has butanoic acid without an H, so it's butanate. Okay, so when you make these, you take an alcohol, pop off the OH, pop off the H, the carboxylic acid, take the carbon group, which is a propyl, combine it with the butanate, and you get propyl butanate. Now the reverse reaction can take place as well. So if you add water to an ester, what happens? It breaks into its original components. Okay, and that's called hydrolysis of an ester. And you can look in the notes. All right, so I'm not going to do the full lecture here. You can do it on your own. Okay. Okay, so there are 3 things that we're going to talk about here before we get into lipids: carboxylic acid esters, polarity, and then molecular interactions, which are related to polarity, and you'll see that in a minute. So what is polarity? Okay, polarity is a really big deal because it relates to molecular interactions, which relates to how molecules form, uh, why we get cells get their shapes, why proteins get their shapes, why soap works, why DNA has its shape. It all ties together. Okay, so what is polarity? Polarity is how the electrons are distributed. The shared electrons are of a covalent bond, how they are distributed between the bonds, between the atoms that are sharing the bonds. Okay, so they could be equally shared or unequally shared. Okay, a polar molecule will have unequal sharing of electrons, and when that happens, one of the parts of the molecule will be more positive, and the other part will be more negative. Okay, so you might have, these are just 2 atoms here, and if it's polar molecule, one set of atoms will have more of the electrons, and the other side will have less electrons. And so it has a plus and minus in. So it has a plus pole and a minus pole. A nonpolar molecule does not have that, where all the electrons of the this is not oxygen. These are just atoms or parts of atoms. This bond here is equally being shared between these two things. Up here, it's unequal. This guy over here has a stronger pull than this over here, and so it makes it polar. Okay. Right. I went over all of this. I talked about it. There's 2 things that determine if a molecule becomes polar or nonpolar, and that's the electronegativity of the atoms involved with the bonds, and the second thing is the shape. All right. So, what you would like to be able to do is if you look at a molecule's structure or its chemical formula to know if it's polar or nonpolar. And there are fancy ways of doing that. And we're not going to do that. We're just going to come up with a quick and dirty way of figuring out if a molecule is polar or nonpolar. Okay. And the two ways are, one, okay, I know I have this here, but what are two ways? Well, the first way is if you're given the structure, which we'll show down here, is that if the center atom has the same things attached to it, it will be polar. Okay, the second thing is if you're not given the chemical structure and you're just given the chemical formula, you can tell if a molecule is polar or nonpolar is if the ratio of carbons is greater than 3 to 1, then it's probably going to be nonpolar. Okay, so I have these four guys here. So let's see if what these four are. So these two here relate to the first one, given the chemical structure. What we do is we look at the center atom. So center atom is carbon, and you notice it has the same things attached to it. They all have hydrogens attached to it, so this will be a nonpolar molecule. Okay, now let's go to this. So this is ammonia. You have nitrogen, and it has H and H and H, and it looks like it has the same things attached to it. But if you look, the nitrogen has lone pairs attached to it, so it doesn't have the same things attached to it. Okay, therefore this molecule is a polar molecule. So it's a little bit tricky there. So it does. So you could. I mean, another way this could be polar is if it had, for instance, if you had C, Cl, H, H, and H. This would be a polar molecule because it has a different thing attached to the carbon. But lone pairs are also things. Okay. Now these two guys don't. You're given the chemical formula, so you can't use this over here. So you have to look at the ratio. And so the ratio here is there's 2 carbons for every 1 oxygen. Okay, so the rule is, a thumb, is that if the ratio is 3 to 1 in terms of carbons to oxygen, then it's probably going to be nonpolar. So the ratio here is less than 3 to 1. So you can see, and then we're going to say that it's polar. Okay, now let's go over here. This one has C12O2. So the ratio here is actually 6 carbons for every 1 oxygen. And you can see that's much higher than 3 to 1. So this would be a nonpolar molecule. Okay, so that's what you need to know there. Okay, so let's talk about why we need to know about polar molecules. Okay, nonpolar molecules. So what are molecular interactions? Those molecular interactions are the interactions between molecules. Okay, so remember, a molecule is 2 or more atoms connected by bonds. Okay, and what we're looking at is if 2 molecules see each other, how are they going to interact? Sometimes they're going to like each other and stay real close to each other. Sometimes they're not going to like each other and they're going to repel. And sometimes they don't even care. So so that's what we're going to talk about here. And this actually applies to lots of stuff that we're going to talk about. All right. So what's the difference between interactions between the molecular interactions between solids, liquids, and gases? Okay, solids like ice, okay, and water, and when it's solid, there's a lot of interactions. Okay, For a gas, like steam, there's hardly any interactions at all, and liquid's a little bit in between the two. Okay, now, so we're going to look at the interaction between polar molecules, nonpolar molecules, and polar and nonpolar molecules. And first one, which is the easiest one, is polar with polar. So polar molecules have a plus and minus end, and that's electrical. And they're kind of like magnets. If you put them in together, the negative end of one molecule is going to line up with the positive end of another one. Okay? And so what we get here is what we call electrostatic attraction between polar molecules. And this is called a dipole-dipole interaction. I went over this in the slide in the lectures, and you can go look it up. I don't want to go over it all now, okay? And that explains that. And what's another name for a polar molecule is hydrophilic. All right, what type of interactions when you put two polar nonpolar molecules together? Okay, nonpolar molecules don't have any plus or minuses to attract each other, so there's no real love between them, all right? So what you got to do is kind of help them love each other. And the way you do that is you push them really close together. And when you do that, they actually like each other a lot, and that's called the London dispersion force, which I just call LDF. And I just explained what happens. You just have to increase the pressure, or get them close together enough, and they'll like each other. All right, next one. So this is where you take polar and with nonpolar, and I went through this in the videos. Okay, so basically what happens is, and really the idea is that we're going to put a little bit of oil, which is nonpolar, and put it into a lot of water, which is polar. Okay, and when you do that, the water molecules all look to get close to each other, and what they do is they push, in the long run, they push all the nonpolar molecules, oil, together. And when they push them together, that makes the oil molecules realize they like each other. And that increases their London dispersion forces. So when you put oil and water, it looks like they separate, okay? It looks like the oil and water don't like each other. But what's happening is the water is pushing the oil together, not because it doesn't like it, it's because it likes itself, okay? And it tries to get around it. And when it does that, all those oil molecules, which are hydrophobic, say, hey, I like you, and they stick together. All right. Okay, the way it's typically described is that the oil and the water don't like each other, or nonpolar and water don't like, so water and oil don't like each other, or nonpolar and polar don't like each other. But, that's not really what's happening. So, so what we typically say is that because it looks like the nonpolar guys don't like water, is that we say nonpolar are hydrophobic. Okay, so now we're going to get into lipids. All right, so what you need to know is, first of all, what is a lipid? A lipid is a biological molecule that is nonpolar. That's a lot going on there. Nonpolar means a molecule that probably has a lot of carbons. Okay, in relation to the number of hydrogens. There are two types of lipids that we'll be studying: steroids and fatty acids. We'll cover fatty acids first, and then steroids. If you look at two structures, a fatty acid looks like a long chain of carbons, and steroid has that unique ring structure, has 3 different rings. But the main thing, if you notice between the two, they both have a lot of carbons. Okay, what are the 2 parts of fatty acid? One is the long carbon chain, okay, and you can look out in the notes. And when you look at the notes, you'll see this zigzag line where each point represents a carbon, right? And it'll be between 12 and I think it was 18 carbons. And this is the fatty part of the fatty acid. And then it has an acid part, carboxylic acid, all right? And that's why it's called fatty acid, because it has a fat part, has a lot of carbons, and has acid, all right? The four types of molecules that come out of the fatty acids, the first one we'll talk about is waxes. And the second one we talked about is soaps. And then we talked about triglycerides and then phospholipids. And I go over each one of these. I'll review each one a little bit as I go along here. All right, the first kind, first of all, let's study this. Let's get into fatty acids and what they are. There are two types of fatty acids. They're saturated, unsaturated. Saturated, all the carbons in this long tail here will have single bonds, while in unsaturated fatty acids, this long tail will have at least one double bond. Okay, we'll see it like that on a single bond. All right, and what we'll go over is how does that affect the physical behavior of each. Okay, before we go into that, I just want to let you know that, and I said this in the when we covered this already, is that we talked about saturated and unsaturated before. Uh, Saturated means all single bonds, and alkanes were like that, okay? Where alkane had all single bonds between the carbons. Alkenes and alkynes had uh, had at least a double bond and a triple bond. Okay, so saturated means has all saturated with single bonds. Unsaturated means not saturated with single bonds. Okay, so also make sure you know what melting means, because a lot of people get mixed up when they learn about melting. They think it's the molecules falling apart and making atoms and things like that. What melting is when the two molecules that are interacting with each other by whatever kind of force, either dipole, or London dispersion forces, is that when they're hooked together through those interactions, it's really tight. But as you heat it up, and you heat it up enough, they'll start to separate. And that's if you start out with a solid like ice, okay, it has a lot, which I told you it has a lot of interactions, and you heat it up. What that heating is going to do is break up those interactions, and those molecules will separate from each other to a large degree, and you'll get a liquid. Okay, and we're going to talk about that now in terms of fats. Okay, because you can have fats can be solids or they can be liquids, and we'll talk about their transition. Why are some fats easier to turn into liquids when they're solids, and some are harder. Okay, and the key thing with that is, as I went over in the videos, if you noticed that the longer chain fatty acids have a high melting point. That means it takes a lot of energy, okay, this is high melting point, okay? And the reason why it's hard to separate these, so when a fatty acid is a solid, you get a bunch of these guys are all tangled together. The reason they're tangled together is because they got a lot of surface area, which increases the London dispersion forces. Okay, so like if you had long hair, all right, and so the longer the chain, the more tangling effect you're going to have. The shorter chain, you don't get the tangling as much. Now, once you put a double bond on this long chain, what it does, it makes the chain stiffer, and it makes it easier for it to melt because it takes less energy to break apart those interactions. Okay, so long chains have a higher melting point than shorter chains. Saturated have higher melting points than unsaturated because the stiffness factor. Okay, so briefly talk about waxes. Okay, waxes are esters. Okay, they're long chain. They have long chain like alcohols, and uh, then they'll have a carboxylic acid part here. And the key thing about waxes, so is they have lots of carbons. Okay, on both on the side of this thing here. Okay, that means it's very very nonpolar. So if it's nonpolar, water's not going to interact with it very well because well the water's trying to react with itself, and so this is very hydrophobic because it has a lot of carbons, we say, and that do it. So that's all you have to really know about the waxes. All right. Now let's talk about one of the types of molecules that can make from a fatty acid, and that's called triglyceride. Okay. And a triglyceride has two parts to it. All right. It has a glycerol, which you'll just have to memorize that. I mean, it was in the last test too. And it also has three fatty acids coming off of it. Okay. And these connections between the glycerol and the fatty acids are ester bonds. Okay, so actually a triglyceride is an ester made out of an alcohol, glycerol, and three carboxylic acids, which are fatty acids. So 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 what happens? How does this make? How do you make this? Okay, is so you start out with glycerol. I'm not gonna draw this all out, and you start out with your three fatty acids. Okay, and the glycerols will have an OH coming off of it. Here's the OHs. And the fatty acids will have their carboxylic acid parts. Okay. And what happens is these two things break off. Okay, so these things are this and this. This is a H and this is a OH, H and a OH, H and OH. Go back to your notes, go back to the video, see that. And it makes three waters. And in the process, what it does is it connects these guys with the chain, with the glycerol. And so you end up getting three waters plus one triglyceride. Okay. What are the two types of triglycerides? Okay, there's fats and then there's oils. Okay. Fats are triglycerides that are solids at room temperature. Oils are liquids at room temperature. Okay. Fats are traditionally found in animals. Okay. Oils usually found in vegetables. And we're going to go over what makes these different. Okay. Now, what fats have are triglycerides that are mostly made out of saturated fatty acids. So if you look at a fat, so let's say this is a fat, this chain, and this chain is probably saturated. For oils, it's the other way around. These are probably unsaturated. Okay, why do fats have higher melting points than oils? That's because they have saturated fats make up the three saturated fats, all right? And saturated fats have higher melting points than unsaturated fats. What is the name of the reaction that turns triglycerides back into fatty acids and glycerol? So what you can do is you can take your triglyceride, okay, and you can break it back into the glycerol and the three fatty acids, okay? But what you need to do is you need to add water. And if you look at this reaction here, this is the opposite of the reaction we just showed you on the previous page, where you took glycerol plus the three fatty acids to make the triglyceride. This is not an E, and three waters, okay? So the reverse reaction is called hydrolysis. And we covered this in a few slides before when we talked about breaking esters. Okay, so the triglyceride is simply an ester. And so you make it by adding an alcohol and a fatty acid, I mean a carboxylic acid. And to make an ester, you just take the carboxylic acids and the glycerol, and you get your triglyceride, which are ester and water. Right. The key thing is that why do we have triglycerides? Well, triglycerides. Sorry, the sun is kind of messing things up here. Um, well, one of the things that triglycerides do in your body is they store. Um, they're a good way of storing energy when you don't need energy available. So it's good potential energy. Another way things. Sorry about this. I gotta get is triglycerides can be used as energy. Okay, and finally, the third one is that uh, triglycerides can be turned into other molecules. Okay, what is hydrogenation and why is it used? Where have we seen this before? What hydrogenation is you take it's either can be take a fatty acid or triglyceride that has unsaturated fatty acids. So if you take unsaturated fatty acid that has a double bond in it, okay, and let's say this is it right here. Okay, so this is an unsaturated fatty acid, and what happens is if you add hydrogen to this, what it does is it gets rid of this double bond, and you got a saturated fatty acid. All right. Okay. Now, where is this used? Okay, so this is a way that we make we can take vegetable oil, like corn oil or whatever, and we could turn it into a solid and make it like margarine. All right, and that's where it's used is to kind of artificially make fats. Where have we seen this before? Well, we saw in the first test where we hydrogenated alkenes to alkanes. Okay, I'm trying to position myself on the screen so the sun doesn't interfere. It's coming up out of this window over here. It's fairly bright, but it's nice to have this nice window out here. But anyways, so next thing is what is the next type of molecule that triglycerides can be? And I mean fatty acids. And those are soaps. Okay. What soaps are is that they're molecules that have been altered. Their fatty acids have been altered have a polar head and a nonpolar tail. Okay, so if you look at the videos, so it has nonpolar tail and a polar head. All right. Okay, why does the head of the soap molecule interact with water? Because water is polar, and so is the head. Why does the tail not interact with water? Well, because it's nonpolar, and we went over this, as nonpolar substances don't interact with water well. Okay, explain how soap forms in micelle in water, and be detailed. Okay, so remember, what happens when you put soap into water, the tails all come together, they get pushed together because of water. Okay, remember, just like in oil, water pushes oil together. And so when it does that, that makes these guys have really strong interactions with each other. And then the heads interact with the water through uh, dipole interactions. Okay, and so there are two kinds of forces to hold together. So this micelle, it's the tails will form London dispersion forces, and the heads with each other. And the heads, so the tails will form a London dispersion forces with each other after they've been pushed together with water, and the heads will form dipole-dipole interactions with the water. Okay, how does soap clean your hands? Be detailed. Well, when you wash your hands, what happens is the oils of your hands get trapped inside the center, the nonpolar part, because the oils on your hand are nonpolar. Nonpolar interacts with nonpolar, so the nonpolar gets stuck inside the middle. But on the outside will be the water parts, the heads, and that's what connects with the water. And so what happens is that the grease and oil get kind of trapped and hidden inside this inside the micelle, and it gets carried off when you rinse your hands. Okay, the next molecule that you can make out of fatty acids is a phospholipid. What is the similarities and difference between a phospholipid and a fatty acids? So actually, maybe we should say triglyceride here. All right, instead. Okay, a triglyceride has a glycerol and 3 fatty acids. Okay, a phospholipid also has a glycerol, but instead of having 3 fatty acids, it has 2 fatty acids and 1 phosphate. Okay, and this phosphate is polar. So this phosphate ends up kind of looking like soap. It has a polar head and 2 nonpolar tails. And that's this part here. Okay, number 2. What kind of structure do phospholipids form when they put in water? They form layers, and so what happens is they form phospholipid bilayers. Is the tails will interact through London dispersion forces. The heads will interact with water and through dipole-dipole interactions. So inside here, okay, London dispersions actually have 2 types of interactions. They have an interaction at the end, the 2 ends are interacting, and the 2 sides interact. So this London dispersions for the phospholipids are actually stronger than soap because they have more than 1 type of interaction that hold the tails together, end to end and side to side. All right. Where are phospholipid bilayers found? They're found in cell membranes. That's in fact what cell membranes are. Why do cells have membranes? That's to keep the inside of the cell away from the outside of the cell, right? Because the inside of the cell needs to have its own world, that it can do its own job and not have interference from the outside. What is the fluid mosaic model of a cell membrane? Well, when you look at a cell on the outside, you look at it. Okay, it's not just phospholipids. It'll have other parts. It'll have cholesterol, which helps give stability to the cell. It'll have receptors, which will let the cell talk with the outside world. It'll have channels that things can move in and out. Okay. And so the mosaic is all these different things that are attached to it. There's carbohydrates and so forth. You could go back and look at the notes on that. All right, and how do things move in and out of a cell? Okay, one is they can just move in naturally without any help. Whoops. Okay, and those type of molecules go through what we call diffusion, passive diffusion, and they tend to be small nonpolar molecules like oxygen and carbon dioxide. Bigger molecules, they need channels, okay, and these are protein channels where they can move in and out without any resistance, and this is called facilitated transport. And then finally, the some molecules don't get a free ride to go in and out of the molecule. They have to pay, and the pay is ATP. And so this is called active transport. So go back and look at your notes for that. Okay, so we're done with the fatty acids here, and so now we're going to talk about steroids, the other type of lipid. What is the similarities and difference between steroids and fatty acids? Steroids, they both have lots of carbons, which makes them nonpolar. But the difference is that they're structures. All right. What is the main structure of steroids? Okay, so they have those three ring structures. Okay, they're very identifiable. Okay, and so it should be able to recognize steroid. What are some roles of cholesterol? Okay, cholesterol is the main steroid in our body. It's produced and it's the precursor to other steroids like the sex hormones and other steroids, but also can be used for energy and and other things that you can so forth. Read the notes. I don't want to go over all this over again. Go back and look at the notes. So if I'm covering that now, that means you can go back and look what it is. Okay. Okay. So there's not a lot here that you need to know. Okay. Uh, so about the steroids, just kind of have to know their shape and some of their functions. As far as specifically about sex hormones and adrenocorticoids, you just have to know of like, what is testosterone used? What is its role? What is estrogen? What is its role? What is progesterone's role? That I have covered. You don't have to go look it up and on Google or your physiology book. Okay. So and you don't have to draw them. You just have to know the few steroid hormones that I talked about and their roles. Okay, and that pretty much does it for steroids. Okay, the last part is I have the two slides, and I have this slide, and it has two parts to it actually. First part is how do the lipids move around? Once you eat them, and they go in your gut, how do they get to your cells? And there's a problem there because your blood is mostly water, and lipids are nonpolar, and so nonpolar, and so if these nonpolar things went into water, they would clog up, and we'd all die. All right. So that has to be the way that the lipids can move through your blood without the the water in the blood detecting the fats. And the way they do that is that they use these things called lipoproteins, and which is we'll talk about proteins in the next test. And so what a lipoprotein does, kind of like soap, what it does is it hides the triglycerides, cholesterol, and so forth inside the nonpolar center of the lipoproteins. All right. And then what happens is the water and the outside of this lipoprotein is attracted to water. Okay, so water just doesn't recognize that there's any problem with it, and so this thing just moves naturally through water. And then when it gets to the cell, it drops the triglycerides, cholesterols, and so forth into the cell to do their job. Okay, there are three types of lipoproteins. There's chylomicrons and very low density lipoproteins, and their job is basically to move triglycerides, okay, to cells and from cells to other places, and that's for energy. LDLs, low density lipoproteins, their role is mostly to carry cholesterol and some triglycerides to cells for manufacturing uh, steroids and other things. Okay. Now, high density lipoproteins are lipoproteins that go around and inside the inside the blood and looks for any of these, any lipids that have got fallen off the truck, so to speak, got fallen off of the lipoproteins and are lying around stray. And if you get too many of those could all come together and form a plaque on your artery walls, and then you could end up getting a heart attack or a stroke. So what the HDL does is it goes out and it collects these guys and it carries them to your liver, where they get broken down into bile. Okay, how's the lipoprotein similar to my cell? I talked about that up here. All right, now you'll hear. So if you've ever had your blood work done and had a lipid panel done, it will check for your LDLs and HDL and cholesterol levels. Now, remember the key thing here is that this is a diagnostic. Is that they look for levels of HDL and HDL. Often LDLs are called bad cholesterol, and HDLs are called good cholesterol. That's not true, because LDLs are good. They have a purpose. They're not bad. But if you have too much of them, that suggests that you may have too many free lipids floating around your blood. Okay. All right. So that covers the material for this test. And no, remember, this is a review. It should not be used as a substitute for you to go back and study the videos, because I'm just touching on what you need to know. You should do more specific on your own with this. Okay. All right. So that's all.